next talk is going to be given by Matthew Lennard. The title is Fast Feature Recovery for Flux Emergence Forecasting in the Photosphere Using Neural Networks. I'm going to give you a 5-minute warning.
Okay, thank you. Right, hello everyone, thank you for being here, and thank you to the organisers for letting me talk. I think this is my first proper academic talk, so I'm kind of quite nervous. I'm here to tell you a bit about what I've been up to for the last 2.5 years. So I'm a PhD student at Sheffield, so I've been using a mix of sort of deterministic methods and neural networks to try to do some feature recovery. Yes, of course. Thank you. In the past, there's a lot of sort of focus on forecasting flares before they occur, which usually requires sort of identifying an active region, then observing parameters. And then obviously this sort of brings back the term nowcasting, which basically you're making probabilistic claims about what's going to happen, and you have sort of on the order of magnitude of hours to do these predictions. And it was suggested a long time ago that basically these are a cascading avalanche of events, so it's a stochastic process which you need to sort of do analysis on every single part. So it's not a straightforward thing to do. So I want to sort of shift the focus a little bit towards forecasting an active region rather than forecasting flaring events, just to give us a bit more of a buffer in order to actually make these predictions. So just simple bit of physics, we have the ideal induction equation. This basically tells us that the magnetic field is deeply intertwined with the velocity field. So basically, as the velocity field changes, that's going to affect the magnetic field and therefore changes the structure. So if we can understand the velocity field, we should be able to understand something about the structure of the magnetic field and how that evolves in time. The thing that we need now is basically velocity field data, which is sort of hard to get, and there are methods of doing this, and sort of the gold standard at the minute, which is being used everywhere, is this Fourier local correlation tracking. So this basically does it's a correlation tracking method, which I'll describe in a couple of slides. But some friends of mine from this paper, Chan et al., basically use this methodology to reproduce structures in the flow, and then basically show that there is a correlation between the magnetic field and the velocity field, and these structures that they find inside the velocity field. But this is only done on the quiet stun, so I'm extending this methodology onto active regions as well. So, excuse me. So in order to actually obtain these velocity fields, we need some data first to look at where we actually have a full velocity field that we can actually learn from. What we have is this simulation from this team in Japan, Hato and Aijima, and basically I have the surface layer of this information, so I can observe what's happening at the photosphere as the system evolves. But basically this simulates the entirety of the convection zone. A lot of other sort of solar simulations, they will cheat and use a very shallow simulation box and use boundary conditions with a lot of assumptions, whereas this, they just place a flux tube basically very near the tachocline and let that evolve into convection. And then what we see as a result is the pores opening up in the intensity field, which is this top image, and then obviously changes in the magnetic field as well. So the hope is that we can use a neural network to obtain these velocities and understand this relationship. So a little bit about LCT and what this method is actually doing. So the idea is basically you have two images with a small shift. So basically you take time consecutive images, one at time t and one at time t plus delta t. And then you observe shifts in this, and you apply a Gaussian to the image, and then you basically make probabilistic claims about the velocity field, which is matching one image to the other one. So it's quite a noisy method, and it tends to work stronger on sort of larger scale motions. So things on the sort of scale of the supergranules, whereas things on like granule structures, it tends to under and overestimate, mostly here in this paper by Fisher and Welsh in 2008. They showed FLCT basically underestimates everywhere massively. So the question is, with a method like this that has poor performance at the small scales, can we actually reproduce complexity in flows, which we sort of are trying to see during flux emergence? And then also, I've been using this other method, which is developed by Asencio Ramos in 2017. So this is DeepVal, which is a convolutional neural network. I'm not going to pretend like I know every single step of this, so I've just been using this as a tool. So this was trained on 2,500 samples, which are 50 by 50 from the simulation. So I take the surface layer, and I take just the intensity and the Vx and Vy components of data, and I feed this into the neural network, and I train it to recover velocity fields from the intensity map. So this is trained for like 100 epochs, so I think this is sort of like a 3-hour time span that it took to train the thing, and then it reproduces full 1K velocity fields in like 1 to 2 seconds. So it's a very fast method after the initial training period. So the question basically is, how well does this perform compared to the old method that people have been using for quite a long time now? So as we see here, so we've got this large diagram, which is a zoom in of the pore with negative polarity in the simulation. And if we zoom right into the edge of the active region, we look at the divergence map, we can get an idea of the sort of structures present and how well these have been captured. And then also we've got a zoom of the flow lines and then the orientation of the flow next to that. So R2D2 is the original simulation. So it's quite complex. On the boundary of the active region, there's quite a lot of stuff going on. And if you look at FLCT, which is a second image down, if you squint, you might be able to make a claim that this kind of looks like the top one, but I'm not convinced by this. And this is due to the fact that you have to sort of average out the data to clean it out, so you literally only capture the sort of larger scale motions over a longer time. Whereas DeepVel, while in the regions where there's much smaller velocity, it's not actually capturing all the information, it's actually capturing a lot of the complexity of the flow, and there is a strong correlation between the structures that are present in the divergence field, for example. And then just some metrics to just show that I've actually quantified this and not just looked at it. So the Pearson correlation coefficient, which is telling you how much the flows are sort of, how well correlated they are. So as you can see, there's sort of like a 4 times increase in success using the neural network compared to the correlation tracking. And a similar thing with cosine similarity, so we want this number to be close to 1, and it tells you about the alignment of the flow with the original flow. And again, it's sort of like a 2 to 3 times increase in success. So just looking a bit more at the actual data and what's being produced, we can see that basically the distribution produced by R2D2, which is this by DeepVel, which is this red line, is very similar in shape to the one by the original simulation, R2D2, the black line. There are some overestimations happening, but generally the shape of the data is the same, and therefore, as you can see in the divergence field, we are actually capturing a lot of the information, and we expect errors to blow up a bit because we're starting to differentiate our data here. But the general shape of the data is matched, whereas with FLCT, it's just kind of following its own distribution, and it's kind of making, it's giving results that are completely unrelated to the actual flow field. So you can see this in the actual plot. So like the previous talk, there's a relationship where basically if we match the black line, which is the original simulation velocity, we've got 100% success. So this FLCT method is basically favoring one direction, and it's only, it's sort of producing normal distributions about the velocity field, whereas DeepVel is actually learning the information stored in the velocity field, and therefore we're able to capture a lot more information. As you can see, the spread does increase quite a lot as you start to differentiate data, but this is kind of expected, but it's a massive improvement on what we had before using the LCT method. So what signatures are we actually looking for in order to identify things that we can use to maybe forecast flux emergence? So what we're actually looking for is material surfaces or material lines, depending on the dimensionality of the data. So I guess I'm looking for material lines, and basically these are described by interactions between particles in the flow. So you can imagine, just if you've seen any sort of fluid motion before, you can imagine a vortical flow or a shear flow or a saddle flow, something like this. So we want a way of finding these transport barriers because these will determine the overall dynamics of the field, of the velocity field, and therefore the magnetic field. So one such surface is this finite time Lyapunov exponent, and I'll take a couple of minutes just to explain through this. So it looks a bit maybe complicated, but it's simple in concept. So basically, what we want to do is measure the regions of stretching and contraction in the flow. So what we take is our velocity field, this U, which is what we're recovering, and we use this to integrate forward in time to tell us about the position of the particles later in the flow. So basically, we start with a mesh grid of particles, and then at every single particle, we measure the shifts between other sort of neighboring particles, and so using this flow field. And then we find the Jacobian of this, so which tells us how this changes spatially. So it tells us the stretching and contracting in the thing, in the system. So if you find the maximum eigenvalue of this, it tells us about the maximal stretching in the system, which is then used to give the sigma value, which is the finite time Lyapunov of exponent. Yeah, so if you do this in forward time, what you're measuring is, thank you. So if you do this in forward time, what you're measuring is the regions of maximal sort of repelling flows. And if you do this in backwards time, so if you integrate backwards in time, you're measuring repelling flows backwards, which is actually contraction in forward time. So we split our data set into two. We integrate forward on one half of the data, and then we integrate backwards on the other half of the data. So this methodology then produces some lines, which I'll show in the next slide, which basically tell you about where the flows are repelling and where they're contracting, and therefore it describes the overall complexity and gives a general shape to the flow. So what we've done is integrated over two different time steps. So 20 minutes, which gives us sort of features on the scale of granules, and over 100 minutes, so this will give you features on the scale of sort of supergranular sizes. So as you can see, FLCT has not performed at all in the small scales. It's kind of, again, it's done its own thing, but this is kind of to be expected. But what you see is a massive increase in performance using DeepVel, where maybe the FTLE field is not one-to-one, but the sort of major flows are captured. So if you look sort of surrounding the active region, there's this sort of like deep red barrier going all the way around. So what we expect is basically a huge diverging flow to open up as the magnetic field pushes out through the solar surface. And then it's a bit harder to see, but over the magnetic field, you get this contracting flow that goes all the way around the edge. So this is basically, the flows are diverging towards the active region, then contracting and falling into the actual pore. So we see this on both scales. And again, so FLCT produces something which, if you don't look at the others, it looks pretty good, but is actually very little correlation with the original data. So what we're actually looking for is a signal in this that we can track. So if we just look at the active region itself and we plot a histogram of the FTLE value, what we see is basically, so basically where the values are higher and where they're lower, that implies that there's a more complex flow taking place. So basically you've got more contractions and stretching in your flow, and therefore it's doing more complex things. And what you see around the active region is that actually the flow gets less complex. The majority of the FTLE field tends towards zero, and then you get a sort of spiking at this point. So this shows us that there's actually something happening here. So this is something that we can try to measure. And if we track this throughout the actual simulation, so if you look at, sorry, I should mention, so the colors of line, so as before, the red is the original simulation, black is the simulation, red is the neural network, and blue is the correlation tracking method. So again, the correlation tracking method is not capturing any information, and it's, whereas the neural network is actually matching a lot of the trends, especially in the smaller scales. So here we're just looking at the short time integration. And as you see, at start of simulation, there's kind of, it has some kind of shape, and then around zero it starts to spike up at the time of emergence, and then it spikes up massively at the time of peak magnetic flux in the simulation, and then as it decays, it goes back to its original sort of state. So the idea is that we might be able to use this to actually track the formation of an active region, and hopefully with enough precision that we can find out these features forming long before, but this actually needs some further work at the minute. So just to sort of conclude the talk, basically what we've shown is what we know, which is that the, well, so LCT is not good at capturing complex flows on small scales, but DeepVel has actually done very well in tracking these flows. And in the future, I sort of hope to actually try this on nocturnal observation and show that I can maybe track something actually going on inside a real image of the sun rather than just a simulation. So I think this has been done by the guys in Janital. But again, this is just tracking sort of quiet sun information. So yeah, I guess. Thank you very much.
Interesting talk. Questions? Comments? We have time. Kevin?
Thank you. Very interesting, but I was just wondering, do you know why FLCT is doing so poorly within the active regions? And does the situation improve at all if you change the sigma?
So I've played about, I use a parsing code to basically find the optimal sigma and sort of averaging frames. So I ran this between sort of sigma from 2 to about 50 or something, and then over sort of like 5 frames up to like 50. And found that was basically the best that I could do. I'm guessing that the reason that it's actually performing poorly is that the velocities within the active region itself and surrounding the active region are actually quite small, and they're sort of changing very rapidly compared to the rest of the field. So I think the performance is basically just based on the scales of the data. I don't know any sort of deeper reason as to why it might be failing. But if you look at the quiet sun, it does actually improve performance massively, but we're not interested in the quiet sun.
Well, pretty much like every local correlation tracking method, you need to have some contrast between the different structures. So whenever things are smoothed, which is what you get at small scales perhaps, and you do not have, just because of instrumental limitations, then you do not have a good performance. I mean, this is a rule of thumb, pretty much. But when sigma is improved, it might be better. More questions or comments there?
I've got one comment. I know I've read about the Deep Bell, and I've known that it has some problems in even smaller scales. Like it has some troubles with it from turbulence and things like that. So I thought you could also read about an article that Yukio Katsukawa made that created another model that is specifying that turbulent scales. So maybe it could help you also in smaller scales.
Is that the paper that's about multi-scale sort of?
Yeah, that
okay.
one.
I know of the paper. I've not actually read it yet. Yeah.
Yeah, absolutely.
Okay. Great. Thank you.
Yeah.
Any more questions or comments, Shane?
Just a real quick question about so the simulation obviously has a certain time scale, and that's what you use for doing a study.
Yeah.
When you go to real observations, how different is that time scale, and how do you think that will affect?
So it completely depends on the actual observations that you're using. So we're looking at HMI, so you can sort of get it to close, so either, I think it was 90 or 135 seconds on the intensity grams. So it's close enough to 2 minutes. So from what I've seen, in terms of sort of temporal information, it performs just about as well. If you look at the sort of spatial scale, so it does struggle a bit more, because you have to downgrade the data, and then the neural network performs a lot poorer. But that was only training at the same sort of number of epochs and stuff. So if I train it for longer, I'm trying to look at making modifications to the loss function, see if that can improve things. But I've not seen too much improvement yet.
Cool. Thanks.
No worries.
One over there at the end.
I believe my question was already answered.
Okay. Good. All right. Redundancy. Good. Any more comments or questions?
Sorry, on Zoom, I don't know if we're supposed to raise our hands or just shout out. But I have a question.
Yeah.
Okay. Go ahead,
Chris
please.
Pryor. Sorry, thank you. I'm just wondering, with your method, does it use all three components of the magnetic field data at your sort of photosphere, your model photosphere?
So the simulation that I have has access to the full three-dimensional magnetic field and velocity field. I'm not training it on any magnetic features at the moment. I'm just training it on velocity field just to see how the performance goes with that. So it performs very poorly reproducing like the Z, the vertical velocities. The magnetic field, I think it has been shown to do better. But just for the sake of this project, I've not been looking at this. It's something that I'm definitely wanting to look at incorporating in the future. And I'm aware I've got some collaborators that I've been working with where they're working on a physics-informed version of this, where they're actually using the magnetic field and the velocity field to do to sort of use the induction equation as a loss function.
Yeah, I was going to say, I mean, when you're using actual data, of course, you're going to need the magnetic field. So, okay, thank you.
Okay, all right, thank you.
Any more questions? All right. One over there in the middle, and then one on the back.
Thank you very much for your talk. It was pretty much interesting. And actually, I got one idea about your finite time Lyapunov exponent. I really like your. I think it's really physically motivated analysis. And at some point, as far as you detected that maximal Lyapunov exponent is positive, well, we can speak. I mean, it tells you that your system has some chaotic component, of course.
Yes.
And in principle, I think it could be, taken. You can look at the criterion which tells you that you can use another physical advanced technologies, for instance, like hidden Markov chains, in order to analyze the system. Would you kind of think in this direction, hidden Markov chains? Would you?
I'm still looking at the minute. So some colleagues have been doing this FTL analysis for a while, and I've just borrowed their code.
I see.
And I'm looking into actually sort of using this as a metric to do the forecasting. So I actually need ideas. So maybe we should talk in a little bit if you've got some.
Great. Thank you.
Great. Thank you.
And one quick question at the end.
Hello, thank you for your interesting talk. So still one question regarding VLCT accuracy. Well, as it was, I believe, mentioned before, that we all know that the technique is pretty sensitive to the quality of the input data, to the contrast. So still, do you have some insights regarding maybe pre-processing, choosing some parts of the dynamic range, whatever, kind of? So in terms of some initial pre-processing steps to improve the VLCT accuracy?
It's a good question. I haven't done any pre-processing on the data, nor have I looked at that yet. It is something to look at, especially when moving to observation, since working with raw, clean data is a very different beast to working with sort of fuzzy images. But yeah, I'm sort of, I need to start reading up on this stuff for my next step. But so yeah, the answer is no.
Yeah, so indeed, maybe a next step, because everybody is constantly struggling with VLCT, including our group, and kind of getting reliable results.
Okay.
Okay, thank you.
Great, no worries. Thank you.
Well, let us thank Matthew again.